We can see
Okay,
your
yes,
slides.
I'm Anastasia Romanou from NASA Goddard Institute for Space Studies in New York. And also I'm affiliated with the Department of Applied Physics and Applied Mathematics, also at Columbia University. And this work that I will be presenting is in collaboration with several people in my institute, Paul Lerner, Mohammad Irfani, Nicholas Leitman-Nimi, and Gavin Schmidt, and others, of course. So I will start my talk saying that machine learning and artificial intelligence has made a revolution in weather prediction in general, but in particular weather prediction. We have gone very quickly, very long ways. And here I'm showing some examples of like leading models right now producing weather forecasts. These are the AI GFS varieties of models from NOAA, the ECMWF AIFS product, Weather Next, which is the Google DeepMind's weather prediction, and of course NVIDIA's Earth 2. So there's a lot. There are several players, private and government agencies, and they're putting out predictions with using artificial intelligence. And this is the word is that actually these models are quite capable at reproducing what traditional prediction models can in terms of weather. But climate is not weather. Right? We know that forever. And why? Because we are dealing with boundary value problems versus initial value problems, like weather models do. We do out of distribution prediction. We are in a transient climate. Things are changing. We are looking at how things will be changing in the future and long-term changes. There's uncertainty in terms of what the forcings are going to be looking like. And so this out of distribution prediction is not an issue that weather prediction models have to deal with, unless, of course, they are looking at extreme events. Now, we have to observe conservation laws. This is very important for climate models because any kind of a mismatch in short time scales might not play a role in weather prediction, but is magnified due to the long-term scales that we are looking at, and of course, can affect the solutions. Air system models have feedbacks, and these are very important to be taken into account when we are actually trying to predict a future climate state. Feedbacks between the atmosphere, the ice, the ocean, the biosphere. And these are not necessary in short-term predictions, especially if you have data which are you revert to, and data simulation is already taking care of these very short, fast feedbacks. And then, of course, we are interested in explainability. Why? Because we are interested in attribution. You can't have a climate model which is going to predict the future and cannot tell you why it is changing. I mean, that's what we need to know. That's why we are using climate models and mathematical models, PDE-based models. They are able to provide attribution, but which is not necessary, very important in weather models. And of course, there is the computational bottleneck. It's simple. Climate models are very expensive. And here you can see a very quick comparison between weather prediction and climate emulation. The horizons are hours to days for weather prediction, decades to centuries for climate prediction. Primary driver is high resolution initial observations. Climate emulation needs forcing agents, greenhouse gases, aerosols, land use, which are all very uncertain, of course, as we move into the future. The data challenge is we need to interpolate between known states for weather prediction, but we need to extrapolate to unseen, especially changing climates. And of course, the physics strategy is we can in weather prediction, we can tolerate non-conservation, like slight energy drifts, but we cannot do so in climate emulation. And of course, AI is not only used for projections, and that's a very good follow-up to the previous talk, where we need to know what the impacts are. Therefore, we need to know what are the plausible outcomes of climate change. But it's also concerned about a lot of other things. AI is playing a role now in model development, climate model development, through parameterizations, through changes in dealing with data challenges and so forth. But we specifically in this talk, we're going to focus on the building of digital twins, meaning of the Earth, where we can provide robust climate projections. And for that, we propose this an architecture of model climate projection emulation based on the Climate Bench version 1 developed by Watson Paris and presented in 2022, which is and specifically one kind of architecture from the workbench, which is the CNN LSTM hybrid model. And that model, you can see the architecture shown at the top. We get maps, monthly, daily. You decide the annual, the resolution of the forcings that you have in greenhouse gases, emissions by location, and we have time series of maps of aerosols emissions as well. And we can include a lot of other forcings, like, for example, land use change. And we pass them through a convolutional neural network that has several layers. It pulls the data together, extracts features, distributions, and passes them through an LSTM model which categorizes them and provides the temporal dependencies. And at the end, at the output of this serial sequence of filters, we get to maps of different properties like surface temperature, like ocean heat uptake, like land vegetation changes. And you can see the workflow here. The workflow is very basic workflow. We get the input, we optimize the emulator, and based on some already existing climate model simulations, and then we can project into the future. Now, this kind of emulation is always within distribution. That's a great thing about it. We have the very low, we train the emulator on historical, on his single forcing simulations we've already done, with idealized scenarios, but also SSP, the socioeconomic pathway scenarios of CMIP 6, like the low and the very low end and the very high end, 126, and the very contestable SSP 585. So we use these two very low and very high scenarios so that we can we can get within distribution evolution of properties. And that is a very big discussion, what is within distribution and what's not. We optimize on a certain scenario, the SSP 245, which is an average scenario in between. And then we say, okay, we optimize on surface air temperature, and you can see here both the training, all the training data sets in gray, and in green you can see the historical and SSP 245 scenario where we optimize our emulator on. Then we extract this architecture, we keep it constant, and we predict other fields in that we are interested in from the climate system, or we predict unseen scenarios, completely unseen scenarios like the 370 and the 3534 and the 534 scenario, which has an overshoot characteristic. So after 2040, we reduce emissions, implying that we have drawdown of CO2. Now, I claim that this is a physics-informed emulation. Why? Because we are actually training the model on the physics, but that doesn't mean that it is explainable, but certainly it does include plausible physical scenarios, projections and evolution of phenomena. Okay, as you can see here, and please look at, in the previous slide, as you can see here, look at the green in all subsequent fields, look at figures, look at the green line and the black line. And you can see that the green line is what we know as truth, previous simulation, actual simulation, and then in black is the emulator. The emulator, you can see, agrees very well, we tuned it to agree very well with the modeled, with the truth surface area temperature. When we look at that, though, in 2 dimensions, we see that the surface air temperature has some errors around the globe. Mostly they are confined in the North Atlantic subpolar gyre. But still, the values are quite low. The biases are plus or minus, within plus or minus or so degrees of warming. And elsewhere, we have slight cooling effects. I can go into detail if someone is interested what might be happening in the North Atlantic. But the important point is that we want to know how well does this emulator generalize. Okay, we can predict the surface air temperature for the 245 scenario, but what about other quantities? What about, for example, the energy imbalance at the top, the net radiation at the top of the atmosphere? Well, as you can, comparing the green and the black, we are doing pretty well. The same for the net radiation at the surface. We are actually able to predict that pathway as well, or the cloud cover, the wind speed, precipitation, sea ice fraction, ocean heat uptake, all the variables that I'm showing in this figure, we are kind of doing more or less well. Maybe the mixed layer depth has a little bit, in terms of pathways, a little bit of a bias. So trajectories and long-term trends for many fields we can do well, but not so much high-frequency variability. We are missing very much a lot of that interannual variability that we don't have, like volcanoes. Well, we have volcanoes, but we don't have them in the exact location. And anyway, the aim of this, the emulator as a first stage is to look at the ensemble mean. So we are aiming to predict the ensemble mean and not so much the spread or the high resolution effects, because we are driving also the emulator using annual mean fields. Now, of course, we're not doing everywhere well. There are some fields like the potential temperature at 1,000 meters depth in the ocean or the gas exchange of CO2 where we are not actually doing that well. We cannot capture, for example, these non-linear effects, the saturation of the ocean sink, for example, the carbon ocean sink. We cannot capture it very well. We cannot capture the nonlinear response of the deep ocean temperature, which carries a lot of memory, past warming and committed warming. We cannot capture it very well at these depths. But what about unseen scenarios? Unseen scenarios, we also are doing a good job in terms of capturing the past, but there are larger biases now, particularly regionally there, and also in the very far end of the simulations, like the last maybe 50 years of that of the simulation. And we definitely are not able, again, to capture these overshoot scenarios like the 534, which is implying changes in the concentration from the linear trend of greenhouse gases. Very strong change in the concentrations of the greenhouse gases. Looking at extremes, we are again doing a better job capturing the intensity, for example, of the extremes, plus or minus 1 degree C globally, and for the near term, 2040 rather than 2080. Regionally, biases might be, sometimes we are underestimating the intensity, in some places overestimating the intensity of the extremes, but always within a very manageable level of heat, as probably impacts people would tell us. But we're not doing as great job in frequency, and definitely not in duration. The biases now are very large. We are definitely underestimating duration by as much as 10 days, even in the near term. And again, of course, we don't see the extreme. We are not able to capture the tails of the distributions of the extremes. So the extremes of the extremes, which are probably some of the very important features that we would like to be able to capture. So this concludes my talk with some parting thoughts. And I think I did go quite fast. But anyway, well, we want to be refining, obviously, the ModelEMU, the emulator. We're using graph nets or adversarial and diffusion networks, and trying to emulate internal variability, because it is very important. what are the possible different states of a climate that we can get within the same forcing. And of course, we want to apply the ModelEMU for other quite new and exciting possibilities for model tuning and spin-up, for paleoclimate proxy emulation, which is something that nowadays we might be at a better position of doing. Well, component emulation, like, for example, the entire ocean carbon cycle, important elements like carbon export and sequestration, we can do that using emulators. Or we can use change the forcing and add land use change to explore the possibilities of what that driver could bring to the system. We can use emulators, climate model projection emulators, to explore tipping points and in particular early warning signals. We can use them for prediction of impacts themselves, like the ones that Tom was talking earlier. Because we can predict the range of the possible climate outcomes. And then, of course, we can use it for multimodal, using multimodal CMIP type of models to build a global emulator that doesn't depend on only one model, like in this slides here that I showed you, but target and combine different models and therefore get a less biased or a better idea of what are the possible scales of change in the future, temporal and spatial scales in the future. And this work was done with the 2023 funding that we got from the NASA Science and Technology Office. Thank you.
Thank you, Anastasia. Put your hand up if you've got a question. There is actually a question in the chat here. I'll just read it out for you. Jenny Meckin has said, Anastasia, I am curious about the SST errors in the subpolar North Atlantic. Is the emulator capable of simulating the AMOC? Secondly, you showed that the MLD is doing quite well. Is this globally or focused on a specific region?
Okay, yes, so the emulator, so this was the first cut of the emulator, and we wanted to see if what we will get for the features that an impact community would be interested in. We didn't look at the AMOC. It has some, the emulator is not particularly flexible to use different shaped arrays. And so the team is trying now to explore the possibilities of looking at tipping points, including a weakening and a collapse of AMOC. But we believe now, going back to your question about the subpolar North Atlantic, the bias there, the emulator predicts warmer conditions than the model. That's what the positive bias is. So that means that the emulator doesn't, because it's being trained on the entire globe, and it's being trained taking into account other elsewhere relationship between surface air temperature and greenhouse gases, it is not able to reproduce the warming hole region, right? The area of excessive cooling that is associated with, as we believe, with an AMOC weakening, potential AMOC weakening, and that could be would be imprinting it at the surface. So the emulator cannot capture the fact that the subsurface ocean is controlling the surface air temperature at this location. So I think that's what we believe the error is stemming from. Yeah.
Thank you. I've got a quick question, just as a layperson's type question. One of the things you said was that emulators should work, well, could help with some of the research that Tom was presenting, like risk attribution. So I'm just thinking off the top of my head, people have asked me who are nothing to do with climate science, who work in civil engineering, for example, and they're much more interested in what's going to happen in this area, in this region, where we're going to build X, like it could be a reservoir, an airport, housing, a factory. In 15 years, could we get high temperatures or high precipitation, because that'll affect whether we can actually do anything on site. So is that the sort of thing that an emulator you think could help with in future or even now?
Yes, so an emulator would be able to help at that, but of course its fidelity will stem from you will depend on the fidelity of the underlying model that is being trained on, right? But of course, there are a lot of ideas about that in the community, like, for example, training in combination of Earth system model and weather prediction model, or regional models, or training on observations in combination, or let's say bias-corrected Earth system models, and so forth, which are doing, I mean, in any way, right now, isn't that the impacts community? That's what it depends on, bias-corrected CMIP simulations. And so what we are saying is that if we can train on similar products, then we can give a better estimation for a much broader range of scenarios.
Okay, thank you. Thanks very much.